semitone we have the 7 natural notes, which are C, D, E, F, G, A, B. Yeah, they basically, we tend to start on the C rather than A, and there's a bit of a reason for that, which I'll probably get to later. The sharp or flat keys are the black ones, and yeah, so basically, depending on which direction you approach the black key, it's either a sharp or a flat, and it essentially just means it's up or down one semitone. So, and the science or physics part that we introduce here is that an octave represents a doubling of the frequency of the note. So if you look at C5, then that's actually the frequency of C5 is 2 times the frequency of C4. So mentioning C4, if we look at that middle octave in the piano, we see that C4 is the first note of that octave, and that's why we call that note middle C. So I'll move in a little bit closer, and we can have a bit of a closer look at our notes. So when we talk about a musical scale, it's usually a progression of 8 notes which start and finish a full octave apart. So we actually have 12 notes in the octave if we include the both black and white keys. So we're sort of leaving some notes out, and so knowing which notes to leave out is probably the important part. So the most common scale which people use is called the major scale, which, if you want to get technical, is called Ionian mode, and it follows the spacing between the notes of tone, tone, semitone, tone, 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 semitone, which gives you the do re mi scale, which is all called solfege. So hopefully you know what I'm talking about there. Otherwise, you might have to sit through the old Rodgers and Hammerstein musical, The Sound of Music, to actually listen to the song and work out what I'm talking about. So this is where having C as the first or root note of the scale becomes convenient, because when we play the C major scale, we just have to play the white notes. Okay, so we're getting fairly close now. So we've got 2 more things to know, and the first is how the notes between those 2 octaves are spaced. So if we have a little bit of a history lesson, way back when, in the early days of instruments, they used like pure tuning, which just used simple harmonic ratios between the notes, because basically that was the easiest way to tune something by ear. But the issue with that was when eventually you had instruments like organs or pianos that had a fixed range of notes, you couldn't really change the key without things sounding, a bit off. So from about, I don't know, the 1500s, they started what was called tempering the intervals between the notes with the aim of pretty much allowing those fixed pitch instruments to sound pretty reasonable in all keys rather than perfect in only one or a couple of keys. And so this is the concept known as temperament. And there are a few early methods. Probably the most notable was something called well temperament, and which was from about the late 1600s. And so if you're into your classical music, Bach composed a piece called the Well-Tempered Clavier, which basically has passages in all 24 major and minor keys. So it's, yeah, pretty impressive piece of music. So it is interesting to know that if you're listening to music from, anywhere earlier than, say, the 1800s, the note spacing, if it's played on modern instruments, the note spacing is different, and it sounds different to what it would have sounded, subtly, but different from what you would listen to today. Anyway, from the 1800s, pretty much Western music in general, and very conveniently for us mathematicians, it uses something called equal temperament. And that's where we just space the notes equally on a logarithmic scale. And so now we can introduce our maths into that. We know that there's 12 notes in the octave and that the octave is a doubling of the frequency, so now we can pretty much mathematically derive the relationship between any two notes. So the fixed ratio between... Sorry?
Sorry, Peter, I was just going to say an echo from the classroom. When are we ever going to use logs?
Exactly. See, here you go.
Yeah.
I actually had a graph that I forgot to put in this presentation. I think I sent it to you, Brian. But anyway, so the fixed notes, the fixed ratio between the two semitones is the 12th root of 2, or 2 to the power of 1 on 12, which is approximately 1.059. And so based on that, we can now work out the ratio between any two notes, which is essentially 2 to the power of n on 12, where n is the number of semitones between the two notes. So pretty much now we know almost everything. The only thing that's missing now is we need a starting frequency to give us a reference. And so that's a little bit arbitrary. Scientific tuning, or I think it's also called philosophical tuning, uses the middle C, which is our bright yellow key there. It's set to 256 hertz because it's, you know, nicely a perfect order of 2, so all your C's are just perfect orders of 2. Typically though, what we use today most widely, and it's called concert pitch, is the A above middle C, A4, and it's set to 440 hertz. So for our program, what's then important is all we need to really know is how many semitones each note is away from that A key, so that we can, you know, determine the number of semitones. So all we basically need to do is look at say our G3, and we can see that we'll look at that a G note is -2 away from our A note, and it's 1 octave down. So it's 12 times -1 plus -2, and that gives us the total number of semitones that is from A4. And so we get our frequency there that you can see at the bottom of the page, and we end up with 195.998 hertz. The beauty of this is that it works out the frequencies pretty accurately, and so rather than reading from a lookup table where it's an approximation of the frequency, it actually calculates it to whatever the limit is on the calculator that we're using. Okay, so we'll finally have a bit of a look at the code. I'm not sure what sort of programming experience people in the audience might have, but I'm guessing it probably varies from not much to probably pretty proficient. Anyway, some coding niceties to possibly talk about is basically the objective is you want to increase the readability either for the next person who's going to look at the code, or if you're not going to look at it for a long time, then it's useful to have comments in your code and meaningful variable names and indentation, basically just so that when you look at the code it looks reasonable. Also, when you're writing a code that you actually want the user to interact with, it's nice to give them useful messages as well so that they know what's going on. There's also, we use in our, just very briefly, we talk about lists and spreadsheets. So when we reference a cell in a spreadsheet, it's just the name of the column with square brackets and then the row number. If we're referencing an array or list element, then it's the list name and the the index reference. So we also do a little bit of string manipulation, which are mainly picking the left characters or the right characters or characters from inside a string of characters. There's some other useful little commands like dim for dimension, which gives you the length of an array, and given that a string is pretty much an array of characters, then dim works for strings as well to give the length of a string. And there's some various other commands that convert strings to numbers and numbers to strings. That we'll have a look at the code now. And so I'm assuming that should now be up on your screens.
Yep, that's looking good.
Okay. Essentially, the first part of the program is just declaring the variables we're going to use and then displaying the messages so the user knows what this thing is asking them. We give a couple of options, which is, hang on, how did I go back up to the top? I don't know how I ended up at the bottom. We can either read music from the sheet, or we can individually load the notes in. And then, as Brian mentioned, we have this request to get a transpose offset, and that basically it just means that we're going to shift whatever the music that we enter is. We're going to shift it up or down, however many number of semitones, and that way, because sometimes actually when you're playing something and it plays on the hub, it might not sound as good as you possibly want it to, so you can sort of adjust the pitch of how it plays, and that sometimes improves how it sounds. And anyway, then we just use pretty much a big loop that either reads in from the user input, or more conveniently from the spreadsheet. And so you can see here we're reading in a note from the spreadsheet here. So if we look at our sheet, we can see that our column name is called S note or sheet note. So we can basically reference any of those cells by S note with square brackets and then the row number. And so we read in. Now, after writing this program, it all worked very well when I directly wrote the notes into the spreadsheet from TI, but then I thought I'd get clever and paste notes in from, say, an Excel spreadsheet or another spreadsheet, and the TI spreadsheet likes to do something a bit tricky, which is put quote marks around any of the strings. So you can see down here, I've clicked on cell A3, and you can see down the bottom, the actual value of the cell is inverted comma, so double quote D5, double quote, and that threw my program out for a while until I worked out what was going on. So this little passage here, where it's a few if statements, basically checks to see if there's a double quote character, and if so, they're just removed so that it can process the string properly, which is where we're using these the mid command. So it's basically the ORD command basically looks up the ASCII code for a character, and it just happens that the ASCII code for a double quote is number 34. So basically, if the first character is a double quote, then it basically manipulates and pulls out the relevant part of the string rather than tries to. Otherwise, the program just wasn't working properly.
That is a neat thing. Yep.
Yeah.
I've always liked the way we can just copy from Excel into the TI spreadsheet. That's very useful, say if we're graphing data or so forth. But because you're then calling on that in a program, there's been that difference there. But how clever to change it using the ASCII, the ORD command, which I know Peter Fox and I have worked with, and that's been featured in recent webinars as well. The ASCII capabilities of the nspire with commands like ORD.
Yeah.
Yep.
Okay.
Great
so then
idea.
we basically, because the way we've entered our notes is we've used the octave number as a suffix, then we can pretty much just read the rightmost character in that string and convert that using the EXPR, converts a string to a number, and so therefore we get a number value for our octave. And then depending on if we use a sharp or flat note, then essentially all we need to do is just make note of the fact we basically just want to capture the sharp or flat if it's there, and we'll reference that later on. So then basically the rest of the code is then based on just the very first character in the string. So if we look at our notes here, we can see that the first character is just the natural note that we want played. And you can see, here you go, is we've got an F sharp in this note, and so our little code that looked for that second character will reference that later on. So then we end up just with a whole heap of if statements that takes us back, and those numbers that I had that showed the distance of the note away from the A, it basically sets that note order up based on how far it is away from the A. So A being 0, C being -9, etc. Also, because you sometimes in music the silence between the music is important, we use R as a rest, and we use the same format for the duration, and then we also use an exit. So after the last note that we want played, we just use an X, and so that's our exit condition. So when it finally reads an X from the sheet, it knows to drop out. Okay, and so we go down a bit further, and now it's going to adjust that value based on whether it was a sharp or a flat. I think there's some issues working with the actual sharp symbol on the TI sheet. I've got a funny feeling. So you can either use the sharp symbol or a plus symbol for a sharp, a B symbol or a minus symbol for a flat, and then it just adjusts that, adjusts the value. Okay, so then ultimately we want to work out the total number of semitones that the note is away from our anchor frequency, and so we see that it's the octave value referenced back to octave 4 multiplied by 12. Then we add our offset for the note and the sharp or flat, and then we add whatever our offset is that we set as our transpose offset at when we were collecting the initial input. And therefore we can then create our frequency, that note, which is our anchor frequency, or 440 hertz, times 2 to the power of number of semitones over 12. So that's a sort of a pretty nifty way of doing it, rather, so that you really don't have to know any frequency other than 1, which makes it pretty tidy. And then essentially we put a bit of a there's some code for our manual entry of notes, and then we get to actually the end of that loop, and when we play the music, it allows us to put a factor in for the tempo between 1 and 100, where 10 is is real time, one is 10 times the duration, and 100 is 1/10 of the duration. So one is slow and 100 is fast, essentially. And then essentially all we're doing is we're reading through the frequency and duration values that have been loaded into our array or list. So the other thing that's important here is that because we're then looping through and playing lots of sounds, if we just have the loop running, it'll be going far too quickly, and we won't actually hear any of the notes except probably the last note. So what we have to do is we have to use the wait command, which basically just stops the processor, and that duration is the same as the duration of the note. So we basically just wait until the note's finished playing, and then we just loop around again and read the next note. So I hope that makes some sort of sense. Anyway, I thought, okay, we can probably go back and look at, say, playing with the. I'll put our Hey Jude's. Actually, I'll use a different song this time, and we'll play with the frequency, we'll play with the pitch, and we'll also play with the tempo.
So Peter, getting the notes themselves, have you just looked up the songs, or you've taken them from music sheets, or have you ripped them out of MIDI files, or what?
Okay, so here's where I got lazy, because it's nice being able to put the music in, but if you've got something, say like this one that's got a few notes in it, then you it's a bit of a pain to actually type them all in. So I did actually write a program that pulls apart a MIDI file, and then essentially you select which track you want to use, and it extracts the notes in a format that then I can just paste into this program. So
right, because that's something I can imagine that kids would really like to get into. Just grab the MIDI file.
I'll give this one a crack and see if you recognise this.
Okay.
Oh, hang on. What have I done? No, didn't like that because I pulled the because I pulled the cord out before. It doesn't like it. So I'll just have to
reboot our little hub.
I'll have to restart that program.
So viewers might be able to recognise the tune from looking at the frequencies. If so,
if they're very quick and very if anyone can name it, I'll be very, very impressed. I'll wait for the comment.
And all good. And of course, we'll need to cross to Foxy fairly soon.
Sorry.
Are you there, Foxy?
A lot of his time already. So anyway, if you've got any requests for a song, then I'll play. I'll try and extract the file, and we'll try and play it after Foxy's done.
Interesting that you mentioned ultrasonic ranger and having the hub listen to that, because I know that Foxy has a particularly interesting application of that in his part of the presentation.
Yeah, I apologise, Peter. I have stolen your time.
That's all right, and I can steal the puns. The fact is, the key for participants to remember here is that if they're flat out taking notes, your programming is very sharp, so if theirs isn't, they can watch the webinar on demand later on. So I'll throw those puns in there, and that'll be it for the puns, I promise. All right, so my session here is just a quick look at a scissor lift which I built with my son just for a bit of fun, and to show you some of the mathematics that we could do some really simple geometry sort of stuff with it, or you can take it all the way through to Year 12 calculus, depending on what you want to do. I have got a little video prepared. I wasn't sure whether or not my webcam would come up tonight, so I pre-tested and put a video in instead. So if we're looking at a scissor lift, which you'll see the actual working model in just a moment, students could look at parallel lines along a couple of different ways and determine whether or not the lines at the top and bottom are indeed parallel, which should be paramount for the safety of said rider. The other possibility, other than geometry, similar triangles within geometry, so there's a couple in here which we can see, and that is key to understanding some of the calculus that's involved as well, if you want to go into that shortly. A bit of trigonometry. We could look at, say for example, the maximum scissor angle. Let's suppose that was 45 degrees, and then determine perhaps say the maximum height of your scissor lift. So something fairly easy for students to do. So what has all this got to do with our little innovator? Let me see if my video's warmed up. Give it a moment, and let's see if it'll play. It had trouble with the controls previously, so let me see if I can get that. There we go. Now, here's our little scissor lift. I know it's a little bit laggy on your screens, but you'll see on the screen in just a moment. I'll pause it when we get to those spots. There's our little servo motor. What I've done is wedged him in between some Lego so that it will drive Lego parts. So all those people that have Lego kits still out there buried away in a cupboard somewhere, I just attached the servo motor, put one of the Lego cogs on there and screwed it in, and that seems to be working quite happily in there. I know that it doesn't have little bumps on it to attach it to Lego, but what I did is just put some little foam, self-adhesive foam strips on it, and that wedged it nicely into the Lego, and that works quite consistently. So we've got a little Lego scissor lift, and that's been driven by our servo motor, which we'll have a look at shortly. The other thing that we've got in there is a motion sensor, so that's measuring the height from the ground up to the actual platform with our little Lego man up there. And the way that's been set up, and this is important for our calculus, is that the X direction as that scissor is closing up is happening at a constant rate. Now we could have driven the thing vertically at a constant rate, but from my model and from analysing other scissor lifts, it tends to be a horizontal drive on these things to give it your vertical lift. They do, a lot of them have hydraulics on them. We don't have little hydraulics here. So what? He's off again. Let's have a look at some calculus that you might use in that one. The motor raises the scissor lift, as you saw, by driving point A towards point B. So it's doing that, let's say, at a constant rate. So a question might be, if the motor does that at a constant rate, how would the height of the platform be changing with respect to time? So let's have a look, and there are multiple ways you could do this. I'm not saying this is the only way to do this problem, but here's one way. So we could say that distance D is constant as a result of our construction, and we stated in the question that the horizontal change in distance versus time is constant. So therefore, let's have a look at some of the things we can derive from our diagram, no pun intended. X would be equal to whatever length D is times cos theta. I've done this in general terms. And Y would be D sine theta. And we can see some Pythagoras there, x squared plus y squared, d squared. So what can we do with all of that? Well, we're required to find the y dt. I don't have any t's in there at the moment, but we'll get there. So we can do a little bit of calculus there. That's about year 11 calculus, particularly if you've got a specific value for d. And then we can get something like that for y. And lo and behold, we can throw the chain rule at it, and we can get the y dx. Which gives us that. The d's cancel out, which is kind of cool. You may also notice that it's kind of in terms of the stuff that we had at the start. The x and the y had references to cosine and sine, and in fact it can be rewritten just simply as negative x over y. So we have an expression for dy dx, but we're required to find dy dt. So let's work with what we've got. We could use the chain rule again. And so if we're trying to find dy dt, that's dy dx by dx dt. And we know that the x dt was specified as some sort of constant. So that does actually make dy dt much easier to work out. It's just equal to negative k, whatever our constant speed was, x over y, with a little negative sign indicating that it's actually slowing down, which it does as it gets higher. It takes off very rapidly at the start, and then as the scissor lift closes up, it reduces the speed, which you'll see in just a moment. If we want to take it one step further, we could write an alternative expression in terms of just x, just replacing the y in there. Or what if we want it in terms of time? We can do that to it, because we can say that the x dt is a constant and therefore anti-differentiate and get an expression for x in terms of time, and now our dy dt is entirely expressed in terms of time. And that's almost the end of our calculus, unless we want to go just a little bit harder on that. Whoops, one step too far. So, just a little bit laggy, folks, sorry about that. We can see that y could also be expressed just in terms of time. The question asks us for the rate, but if we wanted to express y in terms of time, then we've got that expression there. Y equals the square root of d squared minus kt squared. If we start transposing that thing, squaring both sides, we'd have a y squared plus kt squared equals d squared. It's sounding remarkably like an ellipse. So, our little scissor lift went up and down before, and here's the data it collected from our motion detector. Going up and down, you can see its downward motion is a little bit faster than the upward. That's because of the load being placed on the servo. But this curve or data that we've captured here is not looking very linear. In fact, it is part of a curve, as you'll see in just a moment. In terms of the, and I've just dumped the data into a list so you can have a look at it. Kids can work with that. In terms of the actual coding, I'll show you that in just a moment. But that's the coding that was required there. It's not a big program, 35 lines, and a lot of that is just instructional stuff, not actually required to drive it. So in addition to our physical model, we can build a virtual model. Here's our little scissor lift going up and down here.
I like that.
And it's flat out now. There's a copy of the data it collects. So in the perfect environment, we can see that we're getting something resembling an ellipse, but of course students have to be careful. If you have a look at the scale that we have here, our scales are slightly different. So you'd want them to do something like a zoom square or something along those lines to see. Let me see, we've got a zoom square, here we go. But of course I jumped out of my data, so I'd have to zoom out. But rather than wasting too much time here, let's see if we can just zoom in a bit, there we go. It is in fact still looking like a curve. Now the interesting part about that is the actual data, if I only had one layer of our, let me see if I can get him back. He's a little bit hard to grab. Once I put him flat out, I should have had another point. Let's see if I can hang on. I'll just hide that point. Hide that one so I can grab the one I'm after. There's too many points here. Because of my construction, it's all the little joints in the elevator that are stuck in there. So let's go back to our mathematics. Oops, there we are. In terms of the actual code that is sitting behind here, we've got a servo motor which we connected up to the Innovator. Now, a couple of tips here. You must have a battery connected to the Innovator. There's a battery that comes with it when you buy the servo. So you must have that because it draws more power than what your calculator and Innovator can actually supply just running off the calculator battery. So this is one of the experiments where you actually have to have the battery. The other thing that's required is that you must connect it to output 3. So not all the outputs can drive the amount of electricity required from a servo motor. They're a lot more thirsty than a typical motor. You can actually run them out through breadboards and run a lot more servos, but there's a bit more work involved. We're trying to keep it simple. So the first command you've got to throw in is a connect servo, and then you label it. I'll have a look at that command in a bit more detail. So our first command is send set servo 1. This is what I used in the program. So you label it. This is how the command basically works. You label it. We labeled that before as servo 1, so we're talking to it. And then you can decide whether you're going in clockwise direction or counterclockwise. Obviously I used both, one to send it up and the other one to send it down. The next part of the command is the power that you're sending to it. It can go a lot higher than that, but I didn't want to send the little Lego character flying off the top of the elevator when he got to the top or the lift. And then eval T, you can just put a numerical value in there, but I wanted to send it up a certain amount, so or for a certain amount of time rather, so I put evaluate the amount of time that I switched it on for. So talk to that particular servo, what direction, how powerful, and for how long is the guts of that statement there. But the good news is there's a lot of other statements you can use with the servo. Here's another one. Set it to a particular position. Or you can also read it, find its position, which is pretty cool. That's effectively using it as a sensor rather than output. I think that's kind of cool that you can do that. The other device that I had connected to our scissor lift was an ultrasonic motion sensor. It has a basic command that you need to tell it, label it, call it Ranger 1, and tell it where you've plugged it in. I plugged it into input 1. And once you've done that, there's two other commands you need to know, and that is you need to send Ranger 1 and get R. What get R does is basically captures the data, and then obviously you'd probably want to display it on the screen, which is what mine was doing, and then obviously record the data as well. So that was that one, and all of that sits inside that little program. So you can see the first two statements on the send is connecting the servo and then also connecting the Ranger. Then we can start to talk to them. I do a quick talk to the Ranger before I launch into the program just to kind of wake it up, because sometimes it can return unusual values if you don't kind of wake it up first. Then we request how long it goes up and down for, and then away it goes. Whoops. Counterclockwise, 50 for how long, then it waits a little bit, captures some of the motion, and it goes through that loop. And then there's another loop which of course sends it down. So that was it for our Ranger, and I think, Brian, that's just about it for our time as well. So I squashed in as much as I could. Hopefully some people saw that there's a lot of mathematics you can pull out of that, even though it's a really simplistic build. There's a lot of mathematics you can do in terms of geometry, trigonometry, or right through to calculus. So I'll pass it back to you, Brian.
Terrific, and thanks Peter, and thanks Peter. Yeah, I have actually seen that that scissor lift when Foxy has brought it along to show off at conferences that we've been at. We got some interesting comments in the chat there, Foxy. You'll be able to read over those. If you do get the chance to make it along to one of the conferences at MAV coming up, or MAWA in Perth, then there's a fair chance that Foxy will be at both of those conferences, and there's a fair chance he can show you the scissor lift and you can have a play with it. I know also people are looking forward to having a play with this music file when you get it, so look for the follow-up email, look for the download from the website. I've had a heap of fun playing with this, and yes, I've got Hey Jude in it. I'm looking forward to ripping MIDI files and putting it in there. Thanks to one of the participants who suggested we can actually use the microphone to listen to music. So it's, he's working on the idea of playing a piece of music, plugging in a microphone to the hub to listen to the music, and then hopefully strip it into the notes. That would be doing the whole thing there. So here is the program running. No, it's not, because I'm not sharing my screen, am I? I need to do that for you. And So here is the program running. I'm loading the music from the sheet. I can transpose this off, and I'm going to make it a higher pitch. So let's put, what do you reckon, Peter Lannon? Shall I go up 5 for a higher pitch to offset this? Yep.
I have a horrible feeling this might be a football theme song. Would I be correct, Brian?
Oh, no, it's not, Foxy. I'm not clever enough to do that. But it would be good, and Tigerland would be a wonderful thing to play. And hopefully we will be hearing it being played on Friday after the game. But here we go. I've got the tempo for Hey Jude, and I've slowed it down to 30. Let's give that a run. So there we go. And when you get a copy of the file, you'll be able to play at different tempos and different notes. Play at high pitch, play at low pitch, and then you can work on it and see if you can get Tigerland playing. So actually, go back I will go back to my screen. I just want to show just these ones again. Thank you once again to both of our presenters. You impress us with a wealth of clever ideas there. Thank you, Foxy, for the scissor lift. The accolades are rolling in through the chat as I speak. And awesome. Thank you to our special guest presenter coming to us from real industry, the industrial automation engineering, control systems, Peter Lannon from Maitland, New South Wales. And he claims to be part of the solution, not the precipitate. Thank you, Peter.
Oh dear, I'll never leave that one down.
Good evening. And good evening to all.